Hello, everyone, and welcome. Thank you for joining us for this session comparing seismic performance of multifamily structures. As you get settled, a few reminders before we get started. Please do not use the chat box to ask any questions for today's panelists. Instead, use the Q&A. With the Q&A feature, attendees can like a question to move it to the top of the list. And as always, the webinar content and additional resources will be made available online shortly after the session. Today's session, focused on resilient concrete designs, is brought to you by National Ready Mix Concrete Association. This session qualifies for one AIA HSW learning unit for those watching live. AIA California staff will report these units for you once you have finished the session. Now to introduce our presenters. Brandon Ray is a civil engineer with 10 years of experience in the concrete materials and construction industry. In his role as Director of Building Innovations for the National Ready Mix Concrete Association, he promotes concrete and concrete technologies throughout the design community with a special focus on sustainability. Evan Reese is a structural engineer and executive director of the U.S. Resiliency Council, where he works with organizations to promote resilience and improve the performance of our nation's infrastructure in natural disasters. He is a national leader in seismic risk management, publishing more than 50 papers and presenting to groups of building stakeholders around the country. Evan co-founded the USRC in 2011 to educate building stakeholders about the gap between sustainability and true resilient design. Thank you both so much for being here today. And Brandon, Evan, I'll hand it over to you now.
Okay, great. Thank you so much, Sarah. It's wonderful to be here. I really appreciate it. The opportunity to speak again to AIA California, and I'm just going to find my screen right now so that I can share my presentation. Okay, hopefully you can all see my screen. And yeah, so today I'm going to talk a little bit about the U.S. Resiliency Council, but really focus in on a project that we did in collaboration with the National Ready Mix Concrete Association. I think it really has a large impact on California because of its focus on housing, especially on multifamily housing. But to start, let me just give you just a short background on the U.S. Resiliency Council. We're a nonprofit organization. We were started in 2011 by structural engineers, myself included, and folks in the mortgage banking industry, actually. And the idea was that we wanted to really complement what had been occurring over the previous decade with the growth of the U.S. Green Buildings Council and environmental ratings, to include resilience of buildings as part of the discussion around what really is sustainability. And so our primary focus is to develop building performance rating systems for natural hazards, first with earthquake, and we're going to be rolling out wind shortly, and then flood and wildfire. And the idea here is these rating systems, and I'll describe them in a little bit more detail later on, provide building stakeholders with quantifiable metrics about how buildings are expected to perform in natural disasters so that they can be designed to higher performance levels if the owners want that, or there can be meaningful incentives for building owners that retrofit or design higher buildings, either through insurance or lending or other kinds of incentives. We also serve as a certification body for professionals that want to do USRC ratings, similar to the way you might be a lead AP professional. And it's very important for us to be able to demonstrate that everybody benefits when buildings are designed more resiliently, and so that everybody should be willing to invest and collaborate in making them so. We advocate for resilience policies, one of which we recently had a great success in getting $250 million into the California budget for grants to retrofit soft story buildings, soft story apartment buildings. AIA California was a supporter of that, and we're so grateful. And then to partner with industry leaders like NRMCA and others to advance the cause of resilience. Let's see. Okay, so our guiding principle, we call the E4 principle. engineering in the service of equity, the economy, and our environment. It's our belief that as engineers and other design professionals as well, that we can contribute to this concept of good stewardship of our environment, making a resilience good business, but also, being able to focus in on the value that resilience has to all our populations. And so we use this guiding principle in our research, in advocating for policies, and in our educational efforts. Earthquakes have a big impact, obviously, on, the society, the economy, and the environment. The Christchurch earthquake, which was 10 years ago, nevertheless, a fairly recent example of just how dramatic those impacts can be. Big earthquake in Christchurch, New Zealand at the end of 2010 and beginning of 2011. There were two of them. The good news is only 2 buildings in the downtown area collapsed, but more than half of them were ultimately demolished because they were damaged. And that raised a lot of questions about whether, from a code perspective, only having 2 buildings collapse in, what was the big one for them was a very positive thing. But from the perspective of all the owners that lost their buildings, or tenants, or, workers that lost their jobs, their housing, obviously it was a disaster. And so, part of the formation of the USRC was to better align the expectations of population with the design that engineers and architects perform. But also had a really huge environmental impact. We think about deconstruction of buildings at the end of their lifetime. Well, when you have a big earthquake like this, you don't have that luxury. The buildings get demolished, they get hauled off to landfills. There was a 70-foot tall, literally, mound of debris generated from all the debris from this earthquake. And that doesn't even include all the stuff that was hauled off to other islands. And a lot of this stuff includes, toxic chemicals, asbestos, lead, that they just didn't have time to take out. So, building resiliently is also building in an environmentally conscientious way, because you don't have to replace the buildings as often. So, equity, the economy, and our environment. I'm going to say the environment for last because that's going to kind of go into what Brandon's going to be talking about. But when it comes to equity, the idea behind building ratings is that, you can look at a whole community and how different buildings, different services like housing and food are going to perform in an earthquake. You can measure that using rating system like ours. But then you can start into urban planning and start deciding, okay, well, should we have requirements to retrofit older buildings? If we replace buildings over time, should they be replaced once we have the opportunity with higher performing buildings? And so from a community perspective, and I know the architectural profession has always had a really strong interest beyond just the bounds of the building itself, right? They've really tried to look beyond to what kind of impacts their designs are having on neighborhoods and communities. And so from the perspective of the U.S. Resiliency Council, we see this as kind of an opportunity for design professionals when they're working with building owners or jurisdictions to say, hey, if we went a little bit further, design these buildings not just to be safe like the current code, requires, but also to be functional, let's say, after an earthquake, if it's a grocery store or housing, how much better would that be for the community? So we believe that really can target especially areas that are disadvantaged or socially vulnerable. When it comes to the economy, you all know from personal experience, of course, professional experience, that with the advent of the LEED, system and other kind of green rating systems, building owners have that's more desirable for them, right? They can charge more money. It's a more desirable building space. The building's worth more, and so we've seen a lot of evolution from older buildings being either converted to be more LEED or environmentally friendly, or new designs. But we haven't seen that. We hadn't really seen that in resilient design. In Tokyo, the premium for buildings value comes when they are demolished or retrofitted to have really high performing seismic systems like base isolation, since, you know, Japan has so many earthquakes. And so part of our mission is to demonstrate that it can be good for business to build buildings to higher levels of natural disaster performance, and that it can be a supplement to the value you get from, say, designing green. So with that, I'm going to jump into a project that we recently completed. We're very excited about it because, again, it intersects with all three of those elements: environment, equity, and the economy. And that was to look at multi-story apartment building, a standard kind of 4-story multifamily apartment building, built to current code, you know, ASCE 716, but constructed of 4 different types of materials. One with insulated concrete forms, one with traditional stick framing, another with CLT walls and floors, and then one in you know, hot rolled steel, structural steel framing. We looked at these buildings if they were located in Los Angeles, Seattle, and Memphis to look at different construction costs and performance levels based on the seismicity. We estimated construction costs and the performance of these buildings in earthquakes that would, you know, could occur in these 3 areas. Okay, and the goal was to look at 4 buildings that all met the code. They should all be safe. People should be able to get out of these buildings without an issue in a large earthquake, but the performance, nevertheless, might be different. And that's what we wanted to look at. So again, very kind of ordinary style building, you know, double loaded corridor, 4 stories, you know, kind of stucco exterior, nothing particularly special, combination of 1 and 2 story, 1 and 2 bedroom apartments. We looked at the details, of course, of construction for each type of building, whether it be traditional wood framing with joists or and plywood shear walls, steel frames, insulated concrete forms, which had precast concrete floor planks, and then ICF exterior and interior bearing walls. Again, all founded actually on, this is an error. It wasn't found, it wasn't with a brick exterior, it was the stucco exterior. So I apologize for that slide. But basically, develop cost estimates from each of these building types, and then the performance characteristics we measured using engineering analysis. You know, one of the things we found almost immediately was that the cost comparison for these buildings was generally pretty close. There wasn't a great deal of cost differential between the different building types, whether it be ICF, wood, the 2 different wood types, or steel framing. What we did notice, however, though, was that especially this was occurring in, you know, from the start of the pandemic until today, a lot of more variability in some materials. There's a lot of variability in wood pricing, and very little variability over time, in particular in concrete pricing. And so while these buildings are generally fairly price neutral within a few percent, you know, in the middle of 2021, for example, wood was much more expensive than it is even right now. And so that pricing would go up. So from a purely cost perspective, there wasn't a lot of difference in the construction. But in the performance arena, there was quite a bit of difference. I'm showing you 2 graphs here, and it's very simple to kind of look at the 3 different material types, ICF, and then we just sort of combined the 2 wood, the wood types and steel. And the first graph on top is a measure of the strength of the building, right? The stronger a building is, the more capable it is of resisting earthquakes. And again, all 4 of these buildings conform to the code. So it isn't that one wouldn't pass a building department. You know, they're all code compliant. But you can see that the ICF building, the concrete building, is considerably stronger than would an equivalent wood or steel building built to the basic requirements of the code. And that's simply because pound for pound, concrete is stronger than wood or steel. And from a construction perspective, you know, you're going to build the entire exterior of the same material. You're not going to just have little pieces of a concrete wall and then, you know, put wood in between. So you just get more strength naturally as a choice of material. On the bottom is a measure of how stiff the building is, right? So if this is almost looking vertically over the height of the building from the ground to the roof. And in a standard code level earthquake, the buildings are going to move right back and forth. The roof is going to move more than the second floor. And that drift, though, is also, there's an important difference between concrete buildings and the wood and steel buildings. Concrete is a much stiffer material. I probably don't have to tell you that. Foot for foot, right? A foot of concrete walls will be much stiffer than a foot of wood wall or a foot of a steel frame. And so what you see here is a dramatic reduction in how much the building moves based on what it's made of. And that's very important because a lot of elements of the building are particularly subject to movement when it comes to damage. I mean, your structural system itself, whether the plywood cracks or the concrete cracks, but also your partitions, your ceilings, your fenestration, your exterior cladding, all of that is incredibly susceptible to drift. And so the more a building moves flexibly back and forth, the more non-structural damage you're going to get, which can really impact the cost of repair and the time it takes to repair. So for buildings that all meet the code, those made of the stiffer, stronger materials, are demonstrably, quite different than the others. And what this does is this impacts, as I said, the damage and the recovery time. So here are the 3 cities that we looked at: LA, Seattle, and Memphis, and the 4 different building types: ICF, traditional wood frame, CLT, and steel frame. And the top graph looks at the property repair costs in sort of the code level earthquake. These repair costs are a percentage of the replacement cost. Excuse me. So what that means is that in the code level earthquake in Los Angeles, the ICF building suffered damage about equal to 3% of its replacement cost. That's the blue bar in Los Angeles there on the top graph. Whereas a wood building suffered about 9% of its replacement cost. And then the bottom graph looks at how long it would typically take to repair this damage in a way that would allow you to get back into the apartment building and use it as a habitation. Doesn't necessarily mean it's going to be completely repaired, but it'll be habitable. And here there's just a dramatic difference. You can see that the time it takes for reoccupancy in the stiffer concrete building where the non-structural elements are less damaged is really just probably a couple of days. It's probably just the inspection time. But for a very flexible wood building where you have lots of partition damage, ceiling damage, cladding damage, fenestration damage, now you're talking almost 3 months or almost 9 months of time, and that includes all the time for repairs, but also getting building permits, finding contractors. All of that is going to take a lot of time. And you can see for steel, it's sort of in between, but really it's a dramatic difference between if you have a stiff system that just isn't going to cause all of the non-structural elements to be damaged, you're going to save a lot in repair costs and recovery time. And that translates into dollars, of course. So what I've done here is we've taken the average rental cost of 1 and 2 bedroom apartments in different cities, LA, Seattle, and Memphis. And we've said, well, given how long the building will be out of operation for repairs, what's the lost rental revenue that the owner might receive? And we've added that to the cost, the physical damage cost. And so each bar now you can see has a couple of, has property losses and rental losses combined. And again, these are in millions of dollars. Again, the cost to build the buildings wasn't that substantially different because, as a graph I showed previously, but the damage costs are dramatic. You're seeing for CLT, traditional wood framing, costs on the order of $4.5 million in a design level earthquake for Los Angeles, and that's less than about $750,000 for a similar ICF building. So when it comes to the economy, this is really a dramatic indication that you can have two buildings that'll both be safe, but if they're constructed of different materials, they can have a wide impact on the economic value. And of course, what this doesn't include is the social impacts of having renters out of these buildings for many months, right? Depending on whether those are higher income or lower income renters, finding alternative space can be very difficult and have a much, larger socioeconomic impact. And then, of course, again, we didn't look at this in particular, but the damage to the partitions, if the partitions all have to be taken out or the cladding has to be removed and replaced, all that has to go somewhere. And in a large earthquake, when there's lots of buildings in an area damaged, it's not going to be recycled. It's going to be thrown into a landfill. So there's an environmental impact that this has as well. So the USRC rating system, we compared each of these buildings under the USRC rating system. The USRC rating system is focused on three different dimensions: safety, damage, which is the repair cost, and how long it takes to get back in the building. And, similar to LEED, you have different you have different badges that you can get based on the level of performance, right? And so we compared these different building types to how they might achieve a USRC rating. And what we found is that primarily, if you just look at the Los Angeles graph as an example of the first 5 lines there, you've got ICF, wood frame, CLT, and steel frame. You've got safety, damage, and recovery time. They all perform very well in terms of safety, meaning, the buildings are going to be safe. People can get out of the buildings. There's going to be minimal injuries. From the damage perspective, it was, this is just the repair cost. You saw how good the repair costs were for ICF. They're still reasonably good, though, for wood and CLT. But it's when you get to recovery time that you really start to see the difference between the ICF, the concrete performance, and the wood performance. And so whereas an ICF building might be able to get a USRC gold or platinum rating, think of LEED, right? Because of that extended recovery time, the wood buildings would really not perform well. Being down for 9 months is a real hardship, both for the owner and the tenants. And so again, 4 buildings built to the code. The code is a life safety document. They all perform well relative to life safety, but the key difference is in the damage costs and the recovery time. I wanted to thank, of course, NRMCA and the RMC Research and Education Foundation for supporting this work. We also had some help from a local structural engineer, Hobach Lewin, and so I wanted to acknowledge them as well. So to get back, as I sort of wrap up my portion here, we talked so much about sustainability as defining it as green design. And architects, obviously, of course, have led the way in that. And, you made great accomplishments in so many parts of the country in building sustainably. But the challenge is the natural disasters can really put all that at risk. I think Hurricane Sandy, Superstorm Sandy, is a great example of that, and that occurred, 10 years ago now, too, I guess. There are probably more LEED certified buildings in the New York, New Jersey area than almost anywhere. But, over 300,000 housing units were damaged in New York, and, that many in New Jersey as well. There were 10 million tons of debris generated. And, all that debris had to be hauled into landfills where it's leaching chemicals into the air and water. Of course, it all had to be replaced with new materials, right, that also have an environmental impact. So if the buildings had been built as resiliently as they had been built green, then many of them might still be there today. And so, of course, we really can't get to this definition of sustainability without looking at both. So I'm going to leave this to Brandon in a minute, but I just wanted to say that in addition to measuring those 3 dimensions of safety and damage and recovery time, structural engineers are also working to look at how different buildings contribute to carbon impacts at their end of life. That the very rightmost column there where you see the factories, right, is a representation of the repair or demolition of buildings that have been damaged in natural disasters, how that negatively contributes to environmental impacts. And that's an area actually where I think the architectural community and the engineering community can collaborate. You probably have a very good feeling for the embodied carbon of many construction materials. And I know that the engineering community is looking to sort of even improve further our ability to measure performance by including that sort of fourth dimension of environmental impacts. And so, when it comes to construction materials, the big term now is ESG, right? Environment, sustainability, governance. We kind of use the three E's: equity, environment, economy, kind of similar. Adding in resilience to that, ESG plus R is becoming popular now. And, it's about looking at a building over its entire life cycle, right? Construction costs for a resilient building versus a non-resilient building might be slightly more in some cases, not always. But over the life of a building, it's whether it's an earthquake or a hurricane or a flood, it can be the difference between, in small events, a building riding through that completely and not suffering any loss of building operations or damage, versus one that, that is safe, but, can't be reoccupied. It'll go through potentially a large impact in its lifetime where, a resilient building might have to close for a while, but it'll still be repairable. So the owner won't lose their business or their asset. Whereas non-resilient design buildings, they could actually collapse or injure or kill people. And then when we get to the end of life, it's how you choose the end of life for a building. Do you get to deconstruct and recycle a building on your own terms? Or do you have to do it, in a haphazard manner because of a large natural disaster that just destroys the building? So the choice of building material really impacts all these elements of ESG and R beyond just that first cost. So finally, just to say that, the term sustainability that we've been using since the early 2000s has really focused around this idea of carbon. And there's been a lot of studies on, which buildings, materials contribute more carbon to the environment. And that's been a huge amount of focus, but it's been the USRC's goal to look at both, to look at green and resilient design as being two parts of sustainability. You can think of green design is where we have a low impact on the environment, and resilient design is where the environment has a low impact on us. And in the slides that I've shown you, you've seen that you really can't have true sustainability without having both. And so it's our mission to work with engineers, but also with architects, because you're obviously the first line typically when it comes to getting engaged with clients and owners in making that case early on that buildings should be built both green and resilient. We're working on other rating systems. As I mentioned, we have our earthquake rating system. Our wind rating system will be out at the end of this year. We're very excited about that. And then we'll be working on flood and wildfire and likely tornado after that. So our goal is really to expand beyond, the geologic hazard of earthquake into the climate-related hazards, which are the focus of so much attention right now, and a lot of funding too, and interest with, stakeholders, lenders, insurance companies. So with that is my part of the presentation. I know that, again, we've been working with AIA California on our policy initiative, and I've spoken to you all before, and so you're free to reach out to me. We would love to have architectural involvement in the work we do, and particularly as we start developing our flood and our wildfire rating systems. The resilience components of those are much more architectural than they are structural, and landscaping and all of that. So as we start to roll out in development of those, we're going to be going to you to ask for your help on serving on committees and being part of what we do. But most importantly, obviously, When you talk to clients about building design and the value of resilience, I hope you'll use this as a resource and consider, recommending to your clients that they design their buildings to be resilient. So with that, I think that's my last slide. Brandon, if you want to take over.
Perfect. Thank you, Evan. Love always seeing that presentation. So kind of moving forward, it's interesting and sometimes shocking to see the significant variations in displacement periods and also the economic impacts that Evan was talking about. I can't even imagine being displaced for 9 months out of my home, but to take this concept beyond the economical and social impacts and that resilient design can beneficiate, I'd like to now touch on how resilient design can be a sustainability solution. So kind of building off of what Evan was highlighting there at the end of his presentation. So improved disaster resilience and efficient recovery of structures after an event can aid in preventing the unanticipated excess of release of carbon to our environment. And when we look at AIA 2030 and SC 2050, and I think California, meeting in the middle there of sorts to California 2045, the commitments towards reduced emissions and carbon neutrality, it's important to look holistically at our built environment and the prospect of a disaster event having an impact. So when such an event happens, we want to avoid excessive carbon emissions associated with excessive repairs. And from a worst case scenario perspective, we want to avoid total demolition and disposal of a structure as well. So looking at the embodied impacts of those new materials going into the structure, as well as the ones that are being torn out and disposed of. So how does this concept apply to California? Well, looking at FEMA's National Risk Index map, we can see all these lovely shades of red and yellow here. Primary contributing sources of this risk in California are earthquakes and wildfires, but there are other things as well. Looking at a more micro level at just LA County, we can see it contains about 2.5% of the state's land area, but 30% of the state's property value, which would be around $1.9 trillion in this county alone. The corresponding risk index per FEMA for LA County is essentially 100, so maxed out as a very high risk category, or risk index, I should say. And these changes, in concentration of population and property values are significant contributors to the increased human and property loss potential, so those economical and social impacts, but they also can be correlated to significant sustainability impacts as well when you talk about significantly dense populations and built environments in a high risk area. So how do we quantify sustainability impacts? We do this via life cycle assessment. Previously, I think if you sat in on some of our previous presentations, we did do a presentation for California on life cycle assessment of concrete buildings. And I think that's available on their website now if you want to take a look. It is a very broad topic with a lot of variables that go into it. So I'll just do a quick intro here. LCA is the investigation and evaluation of environmental impacts of a product, process, or service. It evaluates all stages of a product's life and considers the interdependence on each stage. And it allows a practitioner to make an informed and responsible and balanced decision to deliver a product with optimized environmental performance. And it looks at everything from the beginning of material extraction to manufacturing, distribution, usage, and end-of-life management as well. So to add to this definition, here is a cost aspect perspective of LCA per MIT's Concrete Sustainability Hub. So the life cycle cost of hazard resilience can be described as the system you see here: build, energy use, wear and tear, hazard repair, and end of life. Hazard repair is where resiliency can predominantly hold an impact, obviously, but technically can also play into durability as well, which would improve other areas of this chain. So these are the stages of the building life cycle. Whole building life cycle assessment allows us to model and estimate emissions associated with each stage. Holistically, embodied carbon includes all of these stages, with the exception of B6 and B7, which is your operational energy and water use. As it pertains to resilience, after a disaster event has occurred, repairing of the structure will use materials and processes that yield carbon emissions, the magnitude of which is directly correlated to the resilient capacity of the structure. So Minimizing repair need will directly reduce the supplemental carbon emissions needed to bring the building back into service. As a worst case scenario, should the structure not be resilient enough, resulting in damages that exceed the acceptable cost of repair, the structure will be demolished and disposed of. This process has a predominantly or potentially significant carbon impacts, but more importantly, the replacement of the structure will yield a duplicating effort. This effort is where the product and construction stages, their emissions will essentially be necessary to occur again. And so the most sustainable structure at the end of the day is going to be the one that you don't have to build twice, but build once. And as Evan touched on with the Christchurch earthquake, upwards of 50% of the downtown structures had to be demolished, which ultimately resulted in new carbon emissions through disposal and replacement construction. So now, what might this, the magnitude of those carbon impacts look like? This is a very, difficult topic to really slice and dice when it comes down to, types of repair materials and magnitude of repairs and things of that nature. But as an example from the USRC study for the Los Angeles area, percent impact can be extrapolated for the different structure types and based upon cost of construction compared to property lost as well. So the resulting impacts range from approximately 3% to 11% among the structure types. So using that as a figure of comparability in terms of percent impact. And when it comes to sustainability, the primary metric is known as global warming potential, or GWP. This is a figure, or this figure itself is reported as a mass of CO2 equivalents per unit area or volume. And using the life cycle analysis that I previously mentioned, a project can have its unit rate carbon emissions quantified. And then purely for estimation purposes, we can level the anticipated percent impact against this to get a general understanding of what the sustainability impacts might be due to an event in the repair and or disposal. So first, a brief example I'll share today comes from an MIT life cycle assessment study on a 12-story commercial structure. In the study, they looked at a 60-year service life of a building when comparing steel and concrete structural systems. The study looked at the embodied carbon per use in this graphic and the operational carbon, which is the use phase carbon. This took place in two different climates to understand the variations of environmental conditions on operational energy, where concrete's thermal mass and improved insulation properties improve the operational efficiency. And this is also something that aligns with the studies via AIA California, or AIA 2030, I should say, where they look at the embodied carbon aspects and also the operational carbon aspects. But zooming out or I should say zooming in and focusing on the initial embodied impacts of structural materials, the study found that concrete buildings had a cradle to grave impact of approximately 193 kilograms of CO2 equivalents per square meter, while the steel building was approximately 232 kilograms of CO2 equivalents per square meter. So extrapolating from our previous study and applying our impact percentage for damage sustained during a design level event, the embodied impacts of repairing the structures to a servable state would be approximately 6 kilograms of CO2 equivalents per square meter for the concrete structure and 25.5 kilograms of CO2 equivalents per square meter for the steel structure. So resilient design directly impacting the end embodied results of these repairs when they're ultimately put into effect. So another brief example we can review and pull data from is a life cycle analysis study performed by MKA structural engineers, where they compared structural systems comprising of glulam timber, steel frame, post-tension concrete, and mild reinforced concrete. Visual representations of these systems you can see here on your screen. This was also in our previous LCA study, a little more in-depth review of the study itself. So review that when you get a chance. Their study did look at and compare the cradle to gate and cradle to grave impacts of the different systems over a 60-year life. So cradle to grave, or cradle to gate, being the initial upfront product emissions. And then the cradle to grave is over the entire service life of the building, not so much from the operational energy, which is excluded from this, but from the use of the materials, repair of the materials, and then disposal of the materials. The ultimate conclusion from the study was that of all four systems, the embodied carbon and overall sustainability impacts were relatively similar, ranging from approximately 180 to 195 kilograms of CO2 equivalents per square meter. As such, choosing a structural system should be based upon application and materials that are most efficient for the intended building use. In an effort to apply perspective to the impacts of damage sustained during a design level event, we can apply our impact percentage against the carbon impact. So in doing so, we can find a theorized sustainability impact in kilograms of CO2 equivalents per square meter of 11.8 for glulam, 20.3 for steel, and approximately 5.2 to 5.5 kilograms for the concrete structures that were studied. Relatively speaking, these values for repair don't necessarily seem astronomical, but circling back to our review of the Los Angeles area, which comprises of nearly $1.9 trillion of property value, you can see that the potential for impacts to ultimately compound significantly. So this is particularly true due to the fact that when an earthquake occurs, and not if, it has the potential to impact a significant and broad area where no structure can avoid the event, right? As such, applying resilient design considerations to your projects can not only mitigate the social and economical impacts, but also significantly beneficiate the sustainability impacts as well. In the end, no community can ever be completely safe from all hazards. Generally, it would be uneconomical to design commercial or residential buildings just to survive a direct blow from a tornado with 300-mile-per-hour winds or speeds, and also magnitude 9.0 earthquake. But resilience does promote greater emphasis on what communities can do for themselves before a disaster hits and how to strengthen their local capacities rather than be dependent on reactive strategies post-event. Ultimately, disasters are inevitable, but their consequences don't necessarily need. So that does conclude our review of resilient design. Both Evan and I can be reached at our contacts here on the screen. I would like to take a moment to build awareness surrounding NRMCA and our Design Assist program known as Build with Strength. We are a grouping of engineers and architects that essentially are a retainer for the industry to support such things as energy analysis, life cycle analysis, specification review, and even cost estimating. So feel free to reach out and we can support you and your teams as needed when it comes to implementing different sustainability strategies or just quantifying overall impacts of a project. So at this time, I'd like to answer any questions anyone may have. And I think, let me see here.
Yeah, I think we had a few questions in the Q&A. I can probably answer the first three.
Yeah.
At least to start. How do U.S. codes compare with New Zealand codes? And somebody correctly said, I don't recall that many buildings having to be replaced from any California earthquakes. Well, California and New Zealand building codes are actually pretty comparable. They're very well considered the New Zealand building codes. They use some different types of materials, but the issue is that New Zealand earthquake, both of them, which occurred literally, I mean, one within a couple months of each other, were like repeats of the 1906 earthquake, the maximum considered event. And we did have a lot of damage, of course, in 1906. Of course, that was a long time ago with old buildings, but we haven't had an earthquake in California, anytime recently that has impacted as many buildings. The 1971 San Fernando earthquake was pretty big, and that had a lot of damage. There was another reason too. I mean, a lot of these buildings were insured, and so even if the damage wasn't so significant, if the buildings had to be torn down, it was actually more economical for them to tear them down because they got insurance. Of course, it ruined the earthquake insurance market there because nobody expected it. But the codes are similar. The second question is a CLT type in the comparison model actually mass timber, glulam wood primary structural members? Yes, so it really was a combination. I mean, there were glulam beams and columns, CLT floor panels, basically. Does earthquake insurance cover damages for recovery and reconstruction? Well, it can. Business interruption insurance is a component of some insurance policies, but only about 10% of either residential or commercial property owners have earthquake insurance. It's very expensive. And one of the big challenges is business interruption. In fact, that can be a very expensive part of the policy because it can be so costly, and you see the kind of downtime that you get. So insofar as you want business interruption insurance, it's all the more critical to be able to control that as best you can, because otherwise it gets to be extremely expensive. There's a question about graphene oxide enhanced cement. Brandon, I'll leave that to you.
Yeah, so graphene oxide enhanced cement. There's also, funnily enough, we just mentioned it briefly, prior to the starting this event, but the titanium dioxide as well. Treatments for concrete are ingredients to be added to concrete that help it react with CO2 in the air, things along that line. But then also the graphene or that type of carbon-based material, which actually can beneficiate the strength of concrete, is another means and methods. But it's it's an additive that helps increase strength. So it's a matter of improving the efficiency of the material. So pound for pound, or I should say strength or per pound of cementitious can be improved, which results in less volume of concrete needed, smaller structural elements, things along those natures, which obviously is a good way to improve your design, make it most efficient use of materials, and reduce the embodied emissions. But then also concrete itself is also a material that does absorb atmospheric CO2 just naturally over time. It's a slow process called carbonation. And it basically turns CO2 into calcium carbonate, which is limestone. That happens, again, over a long period of time at a very slow rate, but it does absorb a significant amount of CO2 over the life of a structure. But in terms of incorporating that into life cycle analysis or whole building life cycle analysis, it is a very complex topic that is getting more refined, every day, essentially. And you'll see it becoming more prominent, in the near future for sure. So next up, I would say, let's see here for you, Evan.
Insurance. So property, it depends. Flood insurance is often required. Wind insurance is often required by lenders. Earthquake insurance, less so because it's difficult to get. On the commercial side, it is sometimes required, but it can be a very costly thing. And the capacity isn't always there. So again, it makes sense to build with the idea of, avoiding needing insurance after the disaster.
Yeah, great. Another question here. So in some of our infill projects, ICF wall thickness is a consideration due to how much space it takes. Any suggestions? There's variations in thickness. Obviously, the ICF does have pre-applied insulation on both sides of the wall, essentially, which adds to the thickness as well. And then, given the seismic considerations and the amount of rebar needed, you can only thin up the wall so much, correct? So it's just a matter of optimizing, maybe improving, the strength ratio, as I mentioned before, of the concrete materials, as well as there are situations where the insulation can be removed if needed, or I know there are products out there that have insulation on one face and then wood forming on another face, things along that nature that might help with that as well. And let's see here. Can you speak to the growing shortage of concrete ingredients such as sand? Obviously concrete is a local material when you look at it. It's using aggregate, which is the predominant volumetric material within concrete. And that's generally a local material, right? You don't want to haul rock or sand across the country for batching a yard of concrete. So it is all relatively local. So this problem does occur more on a local basis, depending where you are. Sand is not so much a problem in too many areas. I know in Texas, it is a common problem, and they use what we call manufactured sand or man sand, which is, basically the fines that are generated from crushing coarse aggregate, basically sieving and grinding or breaking down those smaller materials into a manufactured sand. But it does have, implications on finishability and things along that nature. So there are solutions out there, and you would use a more natural sand for flat work where you're hand troweling it, and then you'd use a manufactured sand for your structural elements like columns and walls. That's an easy way to get around it. But also admixtures these days are always improving to overcome some of the shortfalls of maybe a manufactured sand in finishing by using a finishing aid within the concrete, things along that nature. So overall, there's other things like the cementitious materials, which we talk about sustainable concrete using supplemental cementitious materials that offset the use of a more traditional cement. Overcoming some of that has been, again, regional, as just material availability just varies. But that's where it kind of comes down to fine tuning your mixes and being a little, surgical in what you do and how you use different strategies based upon what's available with the ready-mix producer. And early communication really is key to help locking in those ingredients. Sometimes for larger projects, supply can be locked in as long as the communication's had, on the early end of design, or not design, but coordination, such that you're not waiting to the last minute to source whatever material it is, right? So it is a very complex subject, but we can definitely be a resource to help navigate that as well. Let's see, is there anything else for you, Evan? I don't think so. So I think we're mostly, let's see here, another one just came through. So how can someone participate in the development of the wildfire scoring system?
Yeah.
Go and touch on that.
Yeah, sure. If you have expertise or experience in wildfire, reach out to me. And as we put that committee together, we'd love to have as much help as we can. And yes, we'll be working with some other organizations, specific fire organizations that have a lot of research on fire resistant materials, but also on the science of wildfire spread. So if you're interested, just contact me. And then is the USRC info available as a white paper? I mean, I'm assuming you're meaning about this study. And I believe that studies can be available from the NRMCA. I can work with them about putting it on our website. In fact, I know that we can. So yeah, we have a resources section on our website, and I will post that. That's a good idea. And then on that resources tab, there's also a bunch of other information about our work and what we're doing. Yeah.
Let's see here, there's another question that came in. So is adaptive reuse still cost effective if we are considering new technologies addressing inherent design issues with existing buildings? I would say definitely still effective, right? Obviously it takes a little more pen to paper, right, to figure out the solutions that fit for a building. But we always encourage, reusing and repurposing different elements within the structure, adding in onto the foundation of an old structure such that you're not replacing it entirely. Evan, I don't know if you have any other comments on that.
No, I don't. I mean, it is a challenge, right? I mean, you want to take advantage of all the advanced technology in so many other spaces beyond the structure itself, and that's actually where obviously the architects probably have even greater knowledge on those kinds of things.
Okay, I think that covered most of the questions. If there's anything else, otherwise, thank you, Sarah.
Yes, thank you, Brandon and Evan, so much for your guys' presentation today. For everyone that is on the webinar and has made it this far, AIA California will report your credits, your units to AIA National, and those should be on your transcript within the coming weeks. Thank you to those already who have also reached out to me requesting a certificate of completion. Again, these certificates might take a week or so after the conclusion of today's webinar to be sent out. But if you do require a certificate, you can email me, svasquez, VASQUEZ, at aiacalifornia.org. Thank you again both so much for your guys' time today and presentations, and your resources should be available on our website soon. Thank you, everyone, and have a fantastic day.
Thank you.